Welcome back to the deep dive. We're all constantly plugging things in, using our phones, flipping light switches. Electricity is just what's everywhere. So fundamental, really, that we don't often stop to think about what's really happening inside those wires and circuits. I mean, sure, we might remember basic resistance from school, something pushing back, simple enough. But what if I told you there were other, maybe less obvious forces kind of shaping how that electricity behaves, especially in the stuff we use every day? Forces that, I don't know, affect how clear your music sounds or how efficiently power gets to your house.
That's a really great starting point because you're right, we often picture electricity as just flowing. But it actually faces several kinds of pushback, different layers of opposition, especially with the alternating current or AC that powers most things today. So today, yeah, we're diving into the concept that pulls all these influences together, impedance. And our mission really is to unpack this, make it clear, break down how electricity actually works in circuits, especially if this is maybe new territory for you.
Okay, impedance. Got it. So, starting from scratch then, if we want to understand this bigger picture, where do we begin? What are the sort of basic building blocks affecting that flow?
Exactly. Let's lay the groundwork. Think of three fundamental characteristics in any circuit. First, there's resistance, which you mentioned, probably the one most people know. Then you have the reactor, which you might also hear called an inductor. And third, the capacitor. Now, each of these behaves a bit differently depending on whether we're talking about direct current DC or alternating current AC.
Oh, okay. DC versus AC. That's key, right?
Absolutely. With direct current, that steady one-way flow things are pretty straightforward. Resistance are just resists. It constantly opposes the current, turning electrical energy into heat. Think of it like friction. It's always there.
Okay, simple enough. Resists flow, makes heat.
Then the reactor, which is basically a coil of wire. With DC, once it sets up its magnetic field, it pretty much lets the current pass through without much fuss.
So it does its magnetic thing and then gets out of the way for DC.
Largely, yes. And the capacitor, it's like a tiny storage tank for electrical charge. With DC, it fills up with charge, and then once it's full, it basically blocks any more DC current from flowing through that path.
Charges up, then acts like a dead end for DC.
Exactly. So under DC resistance resists, the reactor makes a magnetic field, then chills out, and the capacitor stores charge, then blocks. Pretty distinct roles.
Right, that all sounds very orderly, predictable even for DC. But then comes the twist, right? Our homes, the grid, that's mostly AC. What happens when the current starts switching back and forth constantly? Do these components stick to their DC jobs, or does the game change?
Yeah, the game definitely changes. This is where things get, well, much more dynamic. Introducing alternating current flips the script for two of our trio. Now, resistance, it stays the course. Doesn't matter if the current is flowing forwards, backwards, fast, or slow. Resistance just keeps resisting, turning energy into heat. It's reliable like that.
Okay, so resistance is still just resistance. Good to know.
But the reactor and the capacitor, they start behaving very differently. Let's take the reactor first. Remember, AC current is constantly changing direction and strength. This causes the magnetic field around the reactor coil to constantly build up, collapse, build up the other way.
Okay, a lot more action than with steady DC.
Exactly. And all this changing magnetic field actually creates a voltage within the reactor itself that pushes back against the very change in current that's causing it. It's called back EMF.
Whoa, so it actively fights the changes in AC.
Precisely. It tries to smooth things out, opposing those rapid shifts. The source material had a great analogy for this. It said, think of it like a car. When it's stopped, air resistance isn't a big deal. But the faster it goes, the stronger the air resistance becomes, hindering the car's movement.
Ah, I like that. So the faster the AC changes frequency, the more the reactor pushes back, like air resistance on a speeding car.
You got it. That's very similar to how a reactor starts to essentially resist electricity more as the AC frequency increases. It's a dynamic opposition.
Okay, that car analogy really clicks. The reactor becomes an active obstacle in AC. Now, what about the capacitor? With DC, it just filled up and stopped the flow. Does it also start, I guess, resisting or reacting to the AC changes? And if both the reactor and the capacitor are now creating this dynamic opposition, do we lump it together? Is there a name for this new kind of pushback?
Yes, absolutely. The capacitor gets in on the action too. With DC, it's charged and blocked, but with AC, the voltage is constantly flipping. So the capacitor is constantly charging one way, discharging, charging the other way,
So
discharging,
it's never just full like in DC. It's always working.
constantly working. And this continuous cycle of charging and discharging creates its own kind of opposition to the AC current flow. It's like it's resisting those rapid voltage swings.
Interesting. So it also hinders the flow, but in its own way.
Exactly. And to your other question, yes, we absolutely need a term for this specific type of opposition that arises in AC circuits from reactors and capacitors. This is where reactance comes in. Reactance is the name we give to the opposition to current flow offered by reactors that's called inductive reactance, and by capacitors, capacitive reactance, specifically when dealing with AC.
Reactance. Okay. Different from plain old resistance.
Very different. Resistance dissipates energy as heat. Reactance involves energy being stored and released in the magnetic field for the reactor, in the electric field for the capacitor. It doesn't just burn energy away in the same way. We use the letter X to represent reactance. And here's a key thing. Just like resistance, we measure its magnitude, how much it impedes the flow, in ohms.
Oh, okay. So it's measured in ohms too, even though it's different from resistance.
That's right. So you've got resistance R, the steady opposition, and now you have reactance X, the dynamic, frequency-dependent opposition from reactors and capacitors that only shows up with AC. Both impede the flow, measured in ohms.
Okay, I think I'm following. We have the constant player, resistance, and then we have the AC-specific players, the reactor and capacitor, whose opposition we call reactance X. Feels like we've assembled the full team now. So how do we talk about the total combined effect? What do we call the grand total of all this opposition in an AC circuit?
Perfect transition, because that's exactly where impedance enters the picture. Impedance is the big one. It's a comprehensive, all-encompassing term for the total opposition to electrical flow in an AC circuit. It accounts for both the steady resistance, R, and the dynamic reactance, X.
So impedance is the whole package deal for AC.
It's the whole package, and it's not some obscure thing. Impedance is a factor in pretty much every AC circuit and component you can think of. We represent impedance with the letter Z, and guess what? Its magnitude, its total opposition, is also measured in ohms.
Okay, Z for impedance, also in ohms, RXZ, all ohms. That helps.
It does help keep things consistent, doesn't it? So connecting it back, if a circuit has a higher impedance, Z, it simply means there's more overall stuff, resistance or reactance, or both, obstructing the flow of AC electricity.
More impedance means harder for the current to get through.
Exactly. So just to recap that key distinction, resistance R is always there, DC or AC. Reactance X pops up only with AC thanks to reactors and capacitors. And impedance Z is the grand total opposition in an AC circuit, combining R and X.
That clarifies it beautifully. R plus X equals Z effectively. Though maybe not simple addition, I suspect.
Ah, you caught that. It's not simple addition because resistance and reactance are a bit out of sync with each other in AC circuits. We actually combine them using vector math, like finding the hypotenuse of a right triangle where R and X are the sides. But the core idea holds. Z represents the total effect.
Okay, vector math. Maybe a topic for another day. But I get the concept Z is the overall result. So we've journeyed from basic resistance through this AC-specific reactance and landed at impedance. Now, the big question, why does this matter to you, the listener? Why should we care about impedance when we're just, charging our phone or using the microwave? What's the practical takeaway?
That really is the crucial question. Why wade through R, X, and Z? And the answer is, well, it's incredibly practical. Understanding impedance helps you understand why your electrical devices work the way they do, especially on AC power. It's not just on-off. Impedance affects how efficiently power gets transferred, how well signals are handled, basically the performance and even safety of, well, almost everything electronic.
Okay, give me some examples. Where does impedance play a role that I might actually notice or benefit from understanding?
There, think about audio. Speakers have an impedance rating, right? Usually 4 ohms, 8 ohms, maybe 16.
Yeah, I've seen those numbers. Never really knew what they meant.
Well, matching that speaker impedance to your amplifier's output impedance is critical. If they don't match well, an impedance mismatch, you can get distorted sound, reduced power output, or even damage your amp or speakers. That's impedance matching in action.
Ah, okay, so that's why you need to check those specs. It's about impedance.
Exactly. Or think bigger picture. Those huge power lines stretching across the country, they transmit power at incredibly high voltages. Why? Partly to minimize current, which drastically reduces power loss due to the resistance and the reactance in the long wires. It's all about managing the line's impedance effectively to deliver power efficiently.
Wow, okay. From speakers to the power grid, that's quite a range.
It really is. Even things like noise-canceling headphones. They use carefully designed circuitry with specific impedances to generate the anti-noise signal correctly, or inside your computer or phone. The tiny pathways on circuit boards carrying high-speed data, they need precisely controlled impedance. If it's wrong, signals can bounce back, creating errors, data corruption, system crashes.
So impedance is critical for digital stuff too, not just power or audio.
Absolutely fundamental. Making sure signals travel cleanly without reflections. It's vital in medical imaging like MRIs for clear pictures, in radio transmitters for efficient broadcasting. The list goes on. It truly underpins so much of modern technology, making sure things work efficiently, reliably, and safely. So understanding it, even just the basics we've covered, gives you a much deeper appreciation for how sophisticated even everyday electronics actually are.
That really drives it home. It's not just theory. It's embedded in almost everything we rely on. We started off wondering about hitter forces in circuits, and wow, we found them. From that basic resistance, we uncovered reactance, this dynamic opposition from reactors and capacitors in AC, and saw how it all comes together as impedance. It's this impedance Z that really governs the flow in our AC world, much more complex than I initially thought.
It is quite elegant when you see how the pieces fit together. So maybe next time you plug something in, or listen to music, or even just see those power lines, take a second to think beyond just the electricity flowing. Consider that invisible interplay of resistance, reactance, and impedance that's shaping its journey, making that technology work. It's a good reminder. Even in things we see every day, there's this fascinating layer of physics quietly doing its job, influencing everything. It really does make you appreciate the engineering behind it all.
A fantastic point to end on. Seeing the unseen physics in our daily lives. Thank you so much for breaking that down for us, and thank you for joining us on this deep dive into impedance. We hope you feel a bit more clued in and maybe even more curious now. Keep exploring, keep questioning, and we'll catch you on the next deep dive.